In this video, we're going to look at Charles's law, which says that the volume is proportional to the temperature at a constant pressure, which directly proportional means that as I increase the volume, the temperature increases, or if I increase the temperature, the volume decreases, or increases. So the opposite is also true. If I decrease the volume, the temperature will decrease. Okay. Again, this is typically how it's given to you on a formula sheet, and this is the form that we will be using it here. And I want to stress that this is at constant pressure. The temperature is in Kelvin, which I did not really cover in chapter 1. We will be reintroducing that in this chapter. And so I have a video of this one. Possibly. There we go.
Charles' law states, at constant pressure, the volume of a given mass of an ideal gas increases or decreases by the same factor as its temperature in Kelvin increases or decreases. If you don't understand that, well, just wait a moment, and we'll show you. First, we're going to put a little bit of water, about a teaspoon, into a soda can. When heated, the water and air molecules inside the can begin to move very rapidly, most escaping the can. Although few molecules remain in the can, they are moving so rapidly that they exert enough pressure to keep the can from being crushed by the outside or atmospheric pressure. Once you see water vapor billowing out of the can, take metal tongs and quickly turn the can upside down and place it in the water. Get ready for a surprise. When the can is placed in the water, the molecules cool, slowing down and condensing. That is, taking up less room or volume. When this happens, they no longer exert enough pressure inside the can to withstand the atmospheric pressure, and a vacant spot is left in the can. The pressure inside and outside the can is no longer equal, and the greater atmospheric pressure crushes the can. Why did you have to turn the can upside down? If you had put the can in upside right, air would have rushed into the can. The pressure would have been equalized and the can would have remained inflated. Putting it upside down in the water is a simple and rapid way to seal the can so that we can observe the effects of atmospheric pressure.
So that experiment is something that can be easily duplicated at home. There are other versions where they put a stopper into that can. Here's another demonstration of that same concept.
This is a beaker full of a little bit of liquid nitrogen. I have
slow internet at my house.
a helium balloon here, and it's not floating because it doesn't have much helium in it, and the weight of the balloon is pulling it down. I'm also going to fill a balloon with my own breath. And then I'm going to dip the balloon in the liquid nitrogen and ask what happens to it. Shrinking. Why? Because it's cooling the air in the interior of the balloon. And in fact, it's kind of crackling and becoming So what happens to helium? Oh, that was with air. This is with helium. Started off a little bit bigger. We're actually running a little low on liquid nitrogen there.
If you'll notice though that the blue balloon has reinflated completely, so it's a completely reversible reaction there. Unlike the can, which because the can's metal, it doesn't reverse. And that one also reinflates. As kind of a joke, when I was your age, I was in a chemistry department that was a little bit bigger than that, and we would go out and do what we call magic shows, which is basically just highlighting principles of chemistry. And this is one that we used to do. We used to do it in a container that you couldn't see inside the container instead of this glass ball. And so before we would start an experiment, especially in a high school, we would typically load a dewar full or that container full of the balloons, and then we would tell them that if they ever wondered what their bean soup was, this is what it was, and we'd bring out the balloons one at a time as they would reinflate. So it's a fun thing to play with. So this is a picture of the textbook that shows you the uninflated and then the reinflated balloons. If you plot the masses and the volumes, so this is temperature and volume, so you have 1 gram, 1 gram, half a gram, and half a gram, so these oxygen, carbon dioxide, and then half a gram of oxygen and carbon dioxide. And they plot it at 3 or 4 temperatures. The oxygen is at 4 temperatures and the carbon dioxide is at 3 temperatures. You see that you get a linear relationship that as the temperature increases, so does the volume, and all of this extrapolates back to one point, and that one point is called a negative 273 degrees Celsius, and this is considered to be absolute zero. For many, many years, it was thought that all movement of all molecules stopped at this minus 273 degrees or absolute zero. However, that has been disproven in recent years of experimentation. They've been able to get within like 0.25 or fourth of a degree of zero, and it now sees a different motion. It's not the typical motion you see with larger temperatures, but there is still motion. So that has pretty much been disproved. But it was based on that theory was based on the fact that all of them, no matter what the mass is or what the compound is, they all extrapolated back to this they all cross zero at the same point of minus 273 degrees. So we'll do an example here of a problem. It says I have a mole of gas. I need a pen back. Okay, so I have a mole of gas. So I have 1 mole of gas. Celsius is temperature, so I have a temperature of 0 degrees C. Millimeters of mercury is a pressure, so I have a pressure of 760 millimeters of mercury. And liters is a unit of volume, so my volume is 22.41 liters. It asks what is the volume, so that's what I'm looking for. If the temperature is 20 degrees C and the pressure is 760 millimeters of mercury. So my pressures are the same, so I'm going to cross those out. The formula was given to you in chapter 1 that the temperature in Kelvin is a temperature in Celsius, and then there's 1 K, there's no degree sign for that, to 1 degree C plus 273. So basically meaning it's a 1-to-1 conversion, but you have to add the 273. So we drop this typically. So to convert it from Celsius to Kelvin, and they have to be in Kelvin forever anytime you use gases. So it's plus 273. So it gives me 273 K here, and then plus 273 here gives me 293 K. So I have 2 temperatures, and I have 2 volumes, or one's unknown. So again, just like when I do Boyle's law, I have to link them, okay? These numbers are all in the same sense, so that typically means that they're linked. So that means my 0 degrees Celsius and my 22.4 is initial, and the unknown and 20 degrees is going to be my final. And the formula is VI over TI is equal to VF over TF. So my initial volume was 22.41 liters. My initial temperature was 273 K. My final volume is what I don't know, so I'll leave that. And my final temperature was 293 K. You can simply just multiply both sides, but I'm going to simplify it one step here by taking 22.41 divided by 273, and I get 0.0821. This number is going to become important shortly. Is VF over 293K. Now I'm going to multiply both sides by the 293, so 0.0821 times 293 is equal to VF. When I multiply those, I get VF is, before I do that, I want to ask myself, what happened to my temperature? My temperature went from 273 to 293. That's going up in temperature. So if the temperature goes up, do I expect the volume to go up or down? And since it's proportional, if the temperature goes up, the volume also goes up. And when I do this calculation, I get 24.1. And the unit has to be the same, and so the K's cancel, leaving me liters, so it's 24.1 liters. We'll come back and do another couple of problems with Charles's law in the next video.